CS 161, lecture number 12, Introduction to Web. Announcements. Okay, that's my new impression. I'll get better at it, but maybe you can tell who it was. Okay, so we have a couple of announcements. Midterm grades were just released about an hour ago. So if you go on Gradescope, you can see how you did on the midterm. And there are also solutions and a blank copy of the exam on the website if you need those. Discussions for this Wednesday and Thursday are canceled. I think the topics got a bit ahead of lecture, so to make things nice and even and also just to give you a bit of a break, those are canceled for this week and they'll start back up next Monday. And someone asked about the stats for the midterm. Those are also on Piazza, so you can go take a look at those. And office hours will still be held this week as usual. So project 2 is the next thing in this class, the next big thing. The design doc draft is due next Wednesday. So this is just a draft of how you plan to design the project. So if you haven't taken a look at project 2 yet, basically project 1 was all about attacking. So we gave you this vulnerable system and your job was to attack it. Project 2 is all about defense. So now it's your turn to write a secure system and it's our turn to try and attack your system. So the first thing you want to do for project 2 is come up with a design as to how you plan to design your system. So my personal recommendation is to start with your design and just try and draw, maybe write in pseudocode at the most, how you want to design your system, and then submit a draft of that. And it's just a draft, so it's only graded on completion. So we're not going to take off points if it's not perfect yet, but we just want to make sure everyone's gotten started on the project, or else it will be quite a crunch if you try to start the day before. So this draft is just to make sure everyone's gotten started and understands what the job is. And then once you have your design ready, then I would say you can start working on code. So that'll be after next week. But for now, I would just think about going over the spec, understanding what the problem is, the tools you have to solve it, and then come up with a draft. So that's the goal. And there's also homework 4, which I think has a couple of warm-up questions for project 2 as well. So they kind of go hand in hand. And that's due next Monday. And since a couple of people asked, there is an optional lab. It is optional, so if you don't do it, it doesn't hurt your grade in any way. But if you are interested, this one's about a padding oracle attack from crypto, and that one's, we just made it to August 11th because it's optional, so just do it whenever you have time. Okay. I think that's basically it. So last time we talked about Bitcoin, if you were here, and the goal of Bitcoin was to design a currency system that doesn't rely on any central authority. So normal money relies on trusting, a bank to take care of our transactions. And if you go and tell the bank, I want to send $1 million to Nicholas, but I only have $10 in my account, the bank is going to say no. But if we don't want to trust any central authority, we have to use cryptography to enforce these rules. Like if I have $10 and I want to send $1 million to someone, I can't do that. So that's our goal. And a couple of things we had to set up before we solved this was, first, we realized that everyone's identity in Bitcoin is their public key. So everyone is identified by their public key, and then they use their private key because they're the only ones who have that private key. So their corresponding public key is their identity. And the way transactions work is everyone signs a transaction with their private key and adds it to a public ledger. And because we want this ledger to be somewhat efficient, every transaction must reference a previous transaction to identify a source of money. So if I want to transfer $10 to Nicholas, I will write, PKP transfers 10 coins to PKN. I'll sign that and I'll put it on the ledger. And additionally, I'll have to say where my 10 coins come from. So my 10 coins come from transaction 10 because someone in transaction number 10 gave me 10 coins. Or my transaction comes from, or my source of money comes from transactions 5 and 9, because in transaction 5, someone gave me 3 coins, and in transaction 9, someone gave me 7 coins, which 3 plus 7 is 10. So somehow I have to identify where my money comes from so that I can pass it forward to whoever's next. And that's how transactions work. And all of these transactions are recorded on a public ledger. So the way the public ledger was designed was it's a hash chain. So basically just a linked list, and every node contains the hash of a previous node. So this gives us a nice append-only structure, because if I change a node, that causes all the future nodes to change, because every node has a hash of the previous node. So if I change node number 3, then node number 4, which has the hash of node number 3, will change. So node number 4 is different now. And then node number 5 has the hash of node number 4. So if I change node 4, then node 5 also changes, and so on. So changing any node will cause the entire chain to change. So that gives us an append-only structure. And this so far is good, but it's still vulnerable to forking attacks. So the attacker can still create their own branch of the chain where they add their own transactions or whatever, and where they change the history of the chain. So that still doesn't quite work because this chain is append-only, but you could have like diverging timelines or diverging histories. So the attacker could create their own chain that has their own history and ignore the real chain. So the way we fix this is called proof of work. And proof of work says, in order to put something on the hash chain, you have to come up with a block whose hash starts with a sequence of n zeros. And usually this is hard, so hashes look random. So finding a valid block that hashes to an output with a sequence of n zeros takes around 2 to the n hashes. So you have to perform some work to put something on the hash. So putting things on the chain isn't free. You have to do a bit of work to put your thing on the chain. And to incentivize people to do this work, we have to give people a little bit of a reward. So if you successfully find a block with a good hash, and that goes on the chain, you can also give yourself a little reward for doing all that work. And the way we prevent forks is we say the longest chain is the true blockchain. So if there are 2 chains, everybody works on the longest one and abandons the shorter one. So everybody goes with the longer chain. This also means if you were trying to make a different chain and try to diverge history, your chain is not going to be the longest one because it's you versus the rest of the world mining on a longer chain. So you are mining alone on your different chain while the rest of the world is working on the other chain. So chances are the other chain is going to have more computing power than you. So they're going to have the longest chain and you will be ignored. But if for whatever reason you have 51% of the world's computing power, so you have more power than the rest of the world combined, then maybe your chain will be longer, in which case you've broken the proof of work scheme. So proof of work does assume that nobody has 51% of the world's computing power so that the longest chain always wins. Okay. So that's the design of Bitcoin. And then we talked a bit about how it's not really that good in practice, or at least that's what we think. And a couple of reasons why are centralization of power. So in theory, Bitcoin is decentralized. So there's no central authority that's controlling the system. So I don't need to put any trust in a central authority. But the problem is in practice, there are actually a couple of groups that have a lot of power over Bitcoin. So for example, there are mining pools where lots of people team up and mine blocks together. And some of these pools control huge parts of Bitcoin. And if they were to team up, it's possible they could have 51%, which breaks the whole assumption. We also have code-based developers. So the people who write the Bitcoin code could always change the Bitcoin code. So that gives them a lot of control. And there are also some things called private blockchains where the only people who can append to the blockchain are trusted people. And that also means you're trusting someone. So private blockchains kind of defeat the point of having decentralized power. There's also pseudonymity. So in theory, Bitcoin says you can only link transactions to your public key because that's how you identify yourself. But nobody knows that this public key belongs to you in real life. So that's in theory, but in practice, it is kind of possible to figure it out. So for example, if you are someone who purchases something every day at a certain time and people can notice your purchasing patterns, they could probably trace your private key or your public key back to you. So it's not fully anonymous because people usually can de-anonymize public keys. And finally, Bitcoin is just hugely inefficient. So sometimes people will be like, what's the runtime of Bitcoin? And there really isn't a runtime. It's not O of n, it's not O of n squared, it's like O of infinity because basically the proof of work scheme requires everyone to waste time hashing things in order to stop attacks. So you are basically sitting there computing useless computations every second of every day of every year just to make Bitcoin work. And it's also inefficient in space. Everyone has to store the entire blockchain in order to verify transactions, which is a couple hundred of gigabytes in size. And it's also just slow. So Bitcoin usually can only process a few transactions per second in the world, which is very, very slow. So it's not efficient. And because it's so inefficient, it also wastes a huge amount of electricity. So we saw that Bitcoin waste about as much energy as like an entire country. So I think Bitcoin miners waste more energy than the country of Sweden or something. And this is all in service of a couple of transactions per second, which is very wasteful. And finally, Bitcoin transactions are not reversible. So if you make a Bitcoin transaction, there's no way to get that money back unless they want to send it back to you. So if someone steals your Bitcoin, you are not getting your Bitcoin back. So that's a problem. So that was last time. And because that was the last crypto topic, we're now finally done with crypto. So if you don't like CS7D math stuff, we're finally out of the weeds there. And today we start web. So this is our third major topic. And today mostly is just an introduction of what is the web, what are the parts of the web, how do things work on the web. And then at the end, we'll briefly talk about security on the web. So that's the plan. Great. So before we start, I guess there's a brief history lesson for you. This is just the history of the web. Basically, the web wasn't designed with security from the start. So the web was designed by, I think, some researchers who were, I guess, finding ways to send information to each other. And they weren't thinking that the web was going to become so ubiquitous, like everyone in the world now uses the web. But at the time, it was kind of just used within universities or between researchers. So when they were designing the web, they did not design it with security from the start. And if you remember your security principles, it's always good to design security in from the start. But because they did not do this, the web has a lot of interesting security vulnerabilities that we have to kind of fix after the fact. So it might be a little clunky, but we have managed to fix most of them. But you'll see that because of historical design decisions, some modern security vulnerabilities exist. So we can see how historical decisions have led to modern vulnerabilities. And we can also see how they make modern vulnerabilities harder to fix. So that's the history lesson. So the idea of the web actually goes back really, really far, much further than I thought. So before the web, there was something called microfilm, and I think some older libraries might still have these. So before computers came along, the best way to store documents in small size, because you didn't have hard drives or the internet or the cloud, you just took your document and you just printed it in extremely small text. So like size 0.001 font, and that's your document. And if it's on a very, very tiny page, like a little card that has like 100,000 words on it, and how do you read this? Because it's so small, you just get a giant magnifying glass to read your microfilm. So before computers, this was the best way to store large amounts of text. And I guess, yeah, modern libraries probably still do this. I've definitely seen these in real life before, so I'm pretty sure they're still around. So yeah, before computers, the best way to store things was just to print it very, very, very small and use a magnifying glass, and that was very space efficient. So yeah, you can fit 100 pages of text on like a very, very tiny, like fingernail-sized piece of film. Now, in 1945, around World War II, people realized this is not the best because you might have piles and piles of microfilm, and it's very hard to sort through them because you can't read them without a magnifying glass. You just have piles and piles of tiny text, and it's very disorganized. So someone came up with this idea called Memex. I guess the name is Vannevar Bush? I don't know. But someone thought about something called Memex, and the idea is let's create this kind of smart mechanized desk for storing and accessing microfilm. So the Memex is like a desk that will automatically find microfilm for you. And the idea for how do you find a piece of microfilm is you give every microfilm a unique trail. So this microfilm is in the history section, it's in the American history section, it's in the 1970s section, it's the Vietnam War or something like that. So you kind of work your way through the trail to find a piece of information. And if you follow a trail, you'll always find the data. So if I always, if I communicate to you that you should go find this information by looking under history, American history, 1970s, Vietnam War, whatever, then you can follow that and find the corresponding piece of data. And you can also create your own personal trails. So if I create a brand new research paper and I want to put it in the Memex, then I create my own trail. So maybe I just wrote a brand new paper on computer security. So I write computer science, computer security, memory safety, whatever, and then put my research paper under the brand new personal trail. And now other people can follow that trail to find that. So this hopefully all sounds familiar to you because this is how the modern web has been created. So modern web has things called URLs and hyperlinks, and that's basically the computerized version of Memex. The second idea is uploading data, which I kind of just touched on, which is if I create my own data, I can use like a photographic hood to make it small and then add it to the collection. And others can use trails to access my data. So that is also how the modern web works. If I want to create a website, now everyone can access my website. Okay. So that's the Memex. And a funny thing about Memex is it sounded great and it was like the pre-internet invention, but nobody actually built one. It was just an idea that people drew out. But because the ideas were so good, a lot of the ideas stuck around when computers came around and people wanted to design the web. So I don't think there are any real Memexes in the world, but the ideas did stick around and now they helped us design the web. Okay. So then came Web 1.0, and Web 1.0 happened around the 1990s and it went until around 2004. So this was kind of the first era of websites. So back in Web 1.0, this was kind of like the next version of Memex, where websites only had static content. There was no code, you couldn't play games on the web or anything like that. It was just static content. So you just use the web to access files. So you had documents, text, image, audio files, and all you could do on Web 1.0 was just access documents, and that was it. So there was no interactive features. You can't play games on Web 1.0. But in 1996, Sun Microsystems, which is a computer company, releases a language called Java. And this is not really that important, but if you want a brief history lesson, basically, if you want to know why there are two languages that are kind of different, and one of them is called Java, and one of them is called JavaScript, the reason is because Java was initially designed to work on lots of systems, including a web browser, but it was too powerful, so they thought, let's not use Java on web browsers, so let's kind of nerf it a little bit, make it less powerful, and that's how JavaScript came to be. So now you know, even though they're not very similar languages, Java and JavaScript. So that's trivia for you if you ever wondered. Okay, and powerful in what sense? I think we can talk about this really soon today, so you'll see. Okay, but yeah, today they don't really share that much, just the name. So, but this is why. Okay, so that's the brief history lesson, and now we're into the modern web. So first we have to ask ourselves, like always, what's the web? So the web is, or the World Wide Web is a collection of data and services. And the data and the services are provided by computers called web servers. So around the world, there are millions of web servers, and they're all providing data to the world. And then you, as a user, use your web browser. So you use Chrome or Firefox, or I hope no one is using Internet Explorer, to access the data on the web servers. So the web servers are out there supplying information to the world, and then you use your browser to go access the data from the web servers. And that is all that the web is, just lots of services that you can access. Now, the web is not the internet. I know a lot of people use these two terms kind of interchangeably, but they're actually not the same. So the internet is actually how data is transported between the server and the browser. So here I just drew an arrow, but we have to actually figure out how this works. So like, do they use wires? Do they use radio waves? Are there any rules for how to send things? So that's the internet, and that's how data is transported. And we're going to deal with that in the next unit, which is networking. But for now, we're just thinking about web. So web is just the interaction between the server, which has services, and the browser, which is requesting the services. And that's it. And for now, we'll assume that there's a magical way to send data between these two people. And then the internet will help us to define how you actually send that data. But for now, we'll just think about the web. Okay. So the goal for today is just to kind of go through all the different elements of the web. And these are the ones that we're going to look at in particular. So first, we have to think about how do you identify a piece of data on the web? That's a URL. How do web browsers communicate with web servers? That's HTTP. And what can you put on a web page? And those are HTML, CSS, and JavaScript. So these might sound familiar, but if not, that's totally fine because we're going to talk about all of them right now. So the first one is URLs, which are a way to identify a piece of data on the web. So URL stands for Uniform Resource Locator, which is not that important. But basically, it's a string that uniquely identifies one piece of data on the web. So this string tells us exactly where something is on the web. And this is, again, if you remember, memex had trails to identify some piece of data in the library. The URL is kind of the same thing. It's a string that tells us where something is on the web. It's a type of a more general construct called URI, which is Uniform Resource Identifier, but that's really not that important. And I think today most people just use these two interchangeably. Okay, so what are the parts of a URL? Well, hopefully everyone has seen a URL. So here's an example right down here. You put them in your web browser, you type them all the time. So hopefully everyone has seen one of these. But now we're actually going to break down what it means. So maybe you've never taken a closer look to see what is a URL and why does it have all these parts. So now we're actually going to see. So the first part of a URL is the scheme. So the way you look for a scheme is you find the double slashes. So there's always a double slash at the start. You look just before the double slash and you find the scheme. So in this case, the scheme is HTTPS. And this scheme tells us, how do you retrieve the data over the internet? So this scheme tells us, when you're sending this data to and from the internet, you should use this protocol to fetch the data. And we'll discuss this a lot more in the networking unit, but there are several different protocols. The two that are important for us are HTTP, which is Hypertext Transfer Protocol, which we'll talk about later, and HTTPS, which is just a secure version that uses cryptography to secure the internet connection. And there are a bunch of other ones too. They're not that important, but you might see them now and then. Sometimes you see FTP, which is file transfer. Sometimes you see file, which is just fetching a file on your computer. Sometimes you see Git SSH for fetching Git repos. And there are a bunch of different ones, but you don't have to know about them. So the only ones you have to care about are HTTP and HTTPS because most of the modern web uses these two. Okay. So the next part comes right after the double slashes. So now we see after the double slashes, there's a couple of different words or phrases. They're separated by dots, and then there's another slash. So in between the double slash and the slash, I get something called a domain. And this domain tells me, remember how we said the web has millions of web servers, and they're all providing data. Well, if I want data, I have to pick one of those web servers to give me the data. So this domain basically tells us which web server to contact. There are a million web servers in the world, and I need to select one, and this domain will help me select one. And the way domains are usually written for humans are as several phrases separated by dots. So in this case, I have one phrase tune, and then one phrase CS161, and then one phrase org. And those are different phrases. They're separated by dots, and that's the domain. Sometimes the domain has some extra kind of weird features on it. So if you generalize it and add some extra information, you get something called a location. So sometimes the location has a username on it if you want to log into one specific user on the web server, but you don't see that too often, I think. But more often, sometimes you see something called a port. So maybe this web server supports several different applications. So maybe I have a web server that's serving Google, and it serves Google Search, Google Images, Google Maps, Gmail, whatever. So this port is a number that comes after the domain that tells us which application I want on the web server. And we'll see more of this again in networking, but basically the idea is it identifies one application if the web server is running multiple applications. Okay, and the final part that is mandatory in a URL is the path. So this comes after the first single slash, and it's the rest of the URL. And this tells us, well, I've picked a web server. I've picked how to contact the web server with which internet protocol. So the last thing I need to ask is, what do I want from this web server? Which file do I want? Which service do I want? So now I'm going to define which service I want on the web server. So if you think about the web server, it's kind of its own computer, and a computer has its own file system. So it has folders and files. So you can think of this as going to the web server and asking it for a file from its own file system. So this can be treated as a file path to ask for a file on the web's file system. So for example, here we're saying we're going to the tune.cs161.org server. So that's the web server on the web that we're asking. And this web server has a bunch of folders and files. So I'm going to ask the server to go into its exorcist folder and find the file avian.html and send me that file. So that's how that works. And if I don't provide a path, maybe I just give it a slash. Well, if you think back to file systems, the slash is kind of the root directory. It's the home folder. So maybe it just asks to return the home folder or whatever's in the home folder. So modern websites often don't just give you access to the file system, and sometimes these paths are interpreted differently. But if you want to think of kind of an abstraction, you can think of it as looking for folders and files. Okay, so those are the parts of the URL that every URL has to have. So every URL always has the protocol and the domain and the path. But there are some kind of extra bonus things that people have added over the years. So one of them is called a query, and this is optional. And if I want to add a query, I put a question mark after the end of my URL, and then I put the query at the end. And this basically says, if I want the web server not to just give me a file, but I actually want a service, I want the web server to compute something for me and give me the result, then I can give the web server some extra arguments so it can process the query for me. So in this case, maybe I'm asking this tune.cs161.org server to draw something for me. So I want to access the draw function. And this function takes some arguments. So I'm going to give it an argument character equals Evan, and another argument size equals big, and I separate them with and signs. And this basically tells the web server, I don't want a file, I actually want a function. And I want the draw function, and I'm going to call the draw function with character equals Evan and size equals big. So the web server will run whatever computation is located at the draw endpoint. So whatever's at the draw path, it's probably a function, and it will compute something with character equals Evan and size equals big and return that to me. So you can think of this as kind of more complicated, fancy web functions that require computation. I can supply arguments if I want to. So that's a query. And the final part is not that important, but it's called a fragment. And this one is kind of just for your interest if you see it in your web browsing days. So this is actually not sent to the web server, and it's just for the web browser's reference. So the most common usage you see here is you tell the web browser to scroll to a part of a web page. So if anyone is like me and spends way too much time on Wikipedia or something, you know how if you click on the table of contents of Wikipedia and it jumps to a section, the way that the jump happens is actually the fragment. So the web server doesn't jump to the section for me, it's the web browser that scrolls down to a given section on the Wikipedia page. So this isn't that important for our security discussion, but if you've ever wondered why there is a hash sign in your URLs, this is why. And sometimes it's used for code purposes, but again, not too important. Okay, so that's the parts of a URL. One final small nit that you have to pay attention to for URLs is that they usually only contain human readable characters, so letters, numbers, symbols, but sometimes URLs need non-printable characters. So maybe I want to supply an argument that has raw bytes or something, or maybe the URLs have special characters that define, slashes are for paths, or the hash sign is for query, or the question mark is for arguments. Sorry, the hash sign is for fragments, and the question mark is for queries. But what if we want to use a special character that's not for a query or for a fragment or for a path? I just want to use it as an argument or something. So then I have to escape my characters, and this is done with something called URL encoding. So URL encoding says, take the character, and if it's not human readable or if it's a special character, then I write the character in hexadecimal and I put a % sign in front, and that lets me encode special characters. So sometimes you see this. I don't know if anyone else was as bored as me as a child, but as a young kid with a computer and nothing else to do, sometimes I would type space bars in the URL just to see what would happen. And I would get these %20s, and I'd be very, very confused as to why my space bars were being %20'd. But now that I've taken this class, I know that %20 is actually the escape of the space bar. So the reason why you see %20s in URLs, if you do, is because the space bar is kind of a special character. URLs don't usually have space bars. So to encode the space bar, I write the hexadecimal with the space bar, which is %20, and then, or I put a % in front of that, and I get %20. If I want the hash sign is %35, I can also encode printable characters if I want to, and I get something like %50 to encode 2 if I wanted to. So we'll see this again later. I know there's a lot of laters, but this is the intro lecture, so that's probably why. But there are some security issues with this. So for example, maybe I'm a web server and I'm trying to block everyone who tries to access the passwords file. But maybe someone is clever and they URL encode the name of the passwords file. And now I have a very hard time telling that this is the passwords file because I have to decode it to see that it corresponds to the passwords file. So that could be a problem, but we'll take a longer look at that later. So hold on to that for now. Okay, I know there are a lot of laters, but I think this is it for URLs. Are there any questions? Okay. So now that we understand what URLs are, we can kind of take a look at how the web works. So again, there's a browser. The browser interacts with lots of different servers, but here's one server for you. This one is www.evanbot.com, which I think actually goes to a spam page, which is kind of funny, but maybe someday we'll buy it with our money and so that it becomes an official Evanbot website. Who knows? But basically, the evanbot.com server has a file system, like we said. So here's the root folder. There's a pictures folder with some pictures inside. There's a secrets folder with some secrets inside. And there's also a couple of functions that you can call to perform some functionality. And these functions will probably be passed to the backend. So the backend is some computing function on the server. So maybe this draw endpoint takes me to the draw function. Maybe the search endpoint takes me to the search function. And they each take in some arguments. So one thing I can do is I can ask for a file. So this is kind of the classic Web 1.0 style URL. So if I say evanbot.com, that's this red arrow because I'm picking evanbot.com server out of the world's millions of servers. I've chosen the evanbot.com server. So the browser will talk to the evanbot.com server using some internet protocol that we'll deal with later. And then now that I know which server I'm talking to, I'm going to find the path. So the path is pictures. So I'm going into the pictures folder and I'm grabbing the evanbot.jpg photo. And that will return the evanbot.jpg photo back to the browser. So that's what the server will do. So that's for requesting files. I can also request functions. So this URL again says, of all the servers in the world, pick evanbot.com. So that's what this arrow is. Then now I'm going to access the draw function. So the draw function, and I'm giving it two arguments. I want bot is Evan and size is large. And this is going to call the backend and say, this server should run the draw function for the user. And it will run the draw function with the user supplied argument, bot is Evan and size is large. It will run that function, and whatever the result is, it will process that result and send it all the way back to the browser. So this is how you would execute, some computation with the server. Okay, again, any questions? One kind of common mistake that I see people make sometimes on projects and stuff is they try to call their own function. So they don't want draw, they don't want search. Maybe they want like delete. So they try to call delete bot equals Evan because they want to delete evanbot or something. But this server is not set up to handle the delete function. There is no delete function. So usually that will just give you an error. Or if I want to find a file that doesn't exist, I want pictures/pintobot.jpg. That doesn't exist. So usually you'll get an error. So usually the server has a defined set of things that are available to the browser, and you have to pick between this defined set. Or if I wanted to do, draw bot equals Evan and size equals large and animated equals true, well, there's no animated argument, so it'll probably be ignored. You usually have to pick from a limited set of functions that is provided to you. Okay, so that's kind of a very simplified view of how the web works. Modern web applications are much more complicated, but that's good enough for us. So the next thing we need to kind of think about is, what is this HTTP protocol? So how does the web browser communicate with web servers? Right, there has to kind of be a structure. I can't just throw random data at the. Whoa! What? Give me a heart attack. Okay. Does anyone know what that was? Okay. Cool. That was just me making sure you stay awake. So anyway, web browsers need a structured way to communicate with web servers. So I can't just throw random data at the web server, and the web server can't just throw random data back at me. I have to figure out a set of rules for how to interpret that data. Right? So if the web server wants to reply with an image, it has to somehow tell me, you are about to receive an image. Or if the web browser wants to give me an error, it has to tell me this is an error. So it needs to somehow give me a structured way to communicate. Otherwise, we're just throwing random data back and forth. So that's what HTTP is. It's a protocol, so a set of rules for how do you request data from the web server and how does the web server give that data back to you. So we want to give it some structure so that we're not just throwing some data back and forth at each other. And there's a secure version of this. So this uses some cryptography at the internet level to secure the protocol as it travels across the internet. And we'll see that later as well. So HTTP, the main thing to know about it is it's a request response model. So the way this works is every request is matched by a single response. Oh, I guess that's it. So it's always one-to-one. So there's no such thing as I make 2 requests and I get 1 response back. That's not how HTTP works. I also can't make 1 request and get 2 responses back. That's also not HTTP. So it's always one-to-one. Now, again, modern applications have gotten fancier and there are some fancy ways to kind of circumvent this. But the most basic model is always a single request from your browser to the server. So I request some information and then the web server processes the request and gives me exactly 1 response back. So it's always one-to-one for our simplified model. So what are the parts of an HTTP request? What do I have to send to the server? Well, the first thing is I have to send to the server the URL path because that identifies what file I want on the server. So first I need to give the path, and I possibly include some query parameters if I want to call a function. Then I have to give a method. So this is something that's kind of new to HTTP. So the method is a category of requests. So requests are separated into several categories. And the method says to choose one of those categories. So the 2 main ones that you've heard of maybe are get and post. So there's HTTP get, which is generally used for requests that don't change the server-side state. So we're not changing any behavior on the server. We're just requesting a file. So give me some information. That's get. There's also post, which says I want to post some information to the server, and that will update the server-side state. So an example of a get request might be, give me this image. When I retrieve an image, I'm not changing any information on the server. I'm just asking it to give me an image. So that would be get. Or maybe if I want to upload a file to the server, so I'm saying, store this file for me, or I'm saying, I want to change my password, so update the passwords file with my new password. That's a post request because I'm giving information to the server. So that's generally how you distinguish get and post. There are some other less used ones, but we're not going to worry about those. And even though this is how it was designed, today, usually GET requests also modify the server side a little bit. So maybe the server is running some analytics, or it's tracking requests, or wants to generate some statistics. So sometimes it will update its server side state a little bit, but generally we still like to separate GET for requests that don't need to change server side state and POST for requests that do change server side state, because that's a little bit better for security, as we'll see later. But generally, all you have to know is GET requests are for things like, give me this file, or give me this picture. And POST requests are for change my password, or delete this file, or delete my account, or something like that. So that's the method, and it's just either GET or POST, so that's it. It's just picking a category. Once you pick the category, you can optionally send some data. And usually GET requests don't send any data, which kind of makes sense, right? Because GET requests say, give me some information. Well, if I'm asking the server for information, I don't have to give it any data because I'm asking the server to give me data. So GET requests usually don't contain any data because I'm asking the server to give me data. So that kind of makes sense. And then POST requests do contain data because I am trying to give data to the server so it can change something on the server. So usually when I'm sending a POST request, I will send some data to the server. If I'm making a GET request, then I do not send any information to the server because I want the server to give me information. So it's kind of the other way around. Someone asked about authenticating a request. That's a really good question. And we have all of tomorrow's lecture about authentication. So I promise you we'll get to that. Okay. And there's also some uninteresting metadata, but if you're interested, there are some headers, and usually it'll also tell us which version of HTTP you're using. But that's not too interesting, so we'll leave it at the bottom. So the main things you care about are the URL path to identify a service or a file on the web server, possibly some query parameters if I'm calling a function. There's a method, so just choose either GET if I don't change state, or POST if I do change state. And then data, which if I'm using GET, I don't send any data. If I'm using POST, then I do send some data. And that's it for requests. And next, we have to think about a response. So how does the server structure its response to us? So again, there's some uninteresting data like the protocol. Then there's a status code. So this is kind of interesting. It tells us what happened with the request. So it's usually a number, and the numbers correspond to things that happen. So some of these might look familiar to you. So there's one called 200, which is everything is good, no problem. Here's a classic one, 403, access forbidden. You are not allowed to access this file. Here's another classic one, 404, this page doesn't exist. So we see that one all the time. And there are a bunch of different ones, but those are some of the common ones. And there's also some data, because usually, regardless of get or post, we usually need some sort of data to return to us. So it can be a web page, it could be an image, audio, PDF, executable, anything can come back to us, and that's in the data. And again, there's some uninteresting metadata, so like the length of the content and stuff. But the main things that come back in the response are a status code to tell us what happened. So did it work? Did it not work? Did I get an error? Which error did I get? And then some data if there is some data. And that's the response. Questions on HTTP? Okay. If not, we can now talk about, there are three main parts of a web page. So there's HTML, there's CSS, and there's JavaScript. And these are usually the main parts of a rich web page. So the first one is HTML. This stands for Hypertext Markup Language. Again, what it stands for is not too important, but basically this is a language that lets us create some structured documents. So the way HTML is structured is it usually has a lot of tags, and the tags are separated with angle brackets. And this lets us create fancier web pages. So I could just send TXT plain text files back and forth on the web if I wanted to, that would be okay. Or I could always send PDFs if I wanted to, that's okay too. But because I want more interesting and interactive web pages, I usually use HTML on the web. And HTML is a language specifically designed to give us fancier web aspects. So for example, the CS161 web page is built in HTML. So when it returns the web page to you and your browser shows you the web page, is actually a bunch of HTML that's displayed in a fancy way. And some of the tags that you might see are the IMG tag for images, or the B tag for bold text, and there's a bunch of different ones. So what can HTML do for us? There's quite a lot. Again, almost every web page that you see is usually based on HTML. So for example, I can create a link. So if I use the A tag, then I get a link. So I say, go to this link, and here's the text to display. So here's a link. If I click on it, it does take you to this web page. What else can I do? I can make a form. So maybe I want to give the user a form to submit. So here's a form. It's a lot of HTML because HTML is kind of a gross language. But if I do it right, then I get this nice looking form. I can fill in my name. I can select my favorite bot, and I can click submit. And when I click submit, because of what the HTML says, it says make a post request to cs161.org/feedback and send the contents of the form in the data of the request. So make a post request with this data that the user filled out in the form. So now the user has a more user-friendly way to send data to servers. So instead of typing in URLs, now they can make a post request, which is nice. Okay. So you can make a form. You can embed an image. So maybe I want to show the user an image on my web page. So I'll use the IMG tag, and I will give it a source. And what the browser will do is it will make a GET request to this source and say, go give me whatever this image is. So it'll automatically make this GET request and show me the image on the web page. So that's nice. I can also embed another web page. So maybe I want to show the user a website inside a website. So to do that, I can use something called an iframe tag. And this says, show me the tune.161.org website inside my website. So now I get an outer website with my stuff, like my text that says website above. And then the inside has the website that you can interact with. So now I have websites in websites. So we won't ask you to remember any of these too much. Like, we're not going to test you and say, what's the HTML for creating an iframe? Because it's not that interesting, and you can usually look that up. But it is good to know what HTML is capable of doing. So here are kind of the powers that it has. Okay. So the next part of the web page is called CSS. So this is usually just to make our websites look a bit nicer. So if I just use plain HTML, I get a very plain looking website. So if you've ever been on a really old website, or I don't know, some professors that are kind of old have very plain websites. That's usually written in plain HTML. But if I want my website to look nicer, then I can add things called CSS, which is a style sheet language for defining how web pages look. So I can say submit button should be blue, or maybe I want, I want this logo at the top of my page, or I want text box to be this color or whatever. So I can choose colors and appearances, and that lets my website look a bit nicer. Now, you don't really have to know how CSS works, but you should know that it's very powerful. And in fact, if you use it maliciously, it can actually be as powerful as JavaScript, which is the next thing we'll see. And yes, if you want to be evil, you can also use CSS to make very ugly websites. So that is something you can do. You can have gigantic yellow Comic Sans text if you want to. That's what CSS can do for you. So the last part of a website that we care about is JavaScript. This is the most powerful part of a website because it's an actual programming language. And this language is used for running code in the web browser. So this is all client-side code, which means it happens on the web browser side. It does not happen on the server side. So the way this works is the server has a piece of code in JavaScript. It saves the code. And if you request that code, it's not going to run this JavaScript. All it's going to do is take the code, package it up, and send it to you over HTTP. And your browser will receive the code, and you are going to run the code yourself. So this is code that you have to run. It's not code that the server is going to run for you. And what this can do for you is you can use it to manipulate the web pages with HTML and CSS. And this lets you create more interactive web pages. If you want to code a game in JavaScript, you could. If you want to make it so that when someone clicks the logo, it starts spinning in circles, you could do that. I'm not sure why you would do that, but you could. So there are lots of different things you can do with JavaScript. And it helps us make modern websites interactive and fancier because now there's a programming language and I can code websites to do different things. But again, this is all run on the browser. So the server is not running JavaScript. It just sends the JavaScript back to you and you will run it yourself. You can also just directly put JavaScript in HTML. And to do this, you just create a script tag and then put the JavaScript inside. Okay. Quick pause if anyone wants to ask questions. Okay. If not, we'll talk about what JavaScript can do. Really quickly, I guess almost every modern browser does support JavaScript. It's almost, I think there's basically no major browser that would not support JavaScript. And again, it's kind of like HTML. You don't have to know JavaScript syntax. So we're not going to test you and say, write JavaScript that does X, Y, Z. But it does kind of help to have a general idea of what powers it has and what it can and can't do. So that's very helpful. And it also helps to know some common attack functions. So attackers often use some common JavaScript functions to execute attacks. So we'll see those. I guess before we do, here's a really quick fact sheet if you're interested in the JavaScript language. Most people tend to agree it's kind of ugly. I kind of agree, but basically it is high level, it's dynamically typed, it's interpreted, supports objects, and it's fast. And it does have to be fast because, again, almost every website uses JavaScript. So people have spent a lot of time and effort trying to make it quick. And one strategy is just-in-time compiling, if you know what it is. That does help you speed up execution. But that's not too important. One kind of important thing, and I'll let you read this on your own time, but basically it's very, very important for the JavaScript compiler in your browser to be secure because your web browser is just another application on your computer, right? It's just like a C program or a Python program. It's just a very complicated one that can access websites. So it's very important that if you're working on Chrome or Firefox, that you don't introduce a memory safety bug in the JavaScript compiler because that could cause very disastrous things. So people who design browsers spend a lot of time making sure that the browsers are memory safe, or else the browser itself could be exploited just like a program, and now people are running vulnerable code in your browser, and that could be very bad. So just something to watch out for if you're ever writing your own browsers, but if not, that's not too important either. Okay, so what can JavaScript do? Well, it turns out almost anything. So JavaScript can modify any part of the web page that you want. You can pick any part of HTML that you want and just change it. So here's my old link. It says it's a link. It goes to tune.161.org. This piece of JavaScript code says, give me the element called link. So the ID is link. So give me the element called link. Change the href link attribute to this URL. And after I execute this JavaScript, the link will change. So now when I click on this link, I'm actually going to go to a different page than if I go to this link. So JavaScript can change anything on the web page that you want it to change. That's pretty dangerous. What else can it do? It can also create pop-ups. So this is a classic one that attackers like to use. So this is a pop-up that shows up, right? And then you have to click OK for it to go away. So when you load this HTML, because it's in script tags, this JavaScript will run and it will cause this pop-up to show up, and now you have to click OK before it goes away. A very good way to annoy users if you want to. What else can it do? It can even create its own requests. So take a look at this. Maybe the server has some HTML with some secret variable inside. So the server has this secret variable. If you're an attacker and I can put my own JavaScript on the website, maybe I will secretly add this JavaScript. And what this says is make a request to the evil.com server, and make a post request. And what do I send? Let me send the secret inside the post request. Well, what happens now is if you control this server, right, which presumably you're the attacker, you control evil.com, you are going to receive a post request. So your web server will see a request come in with the secret. And now you've learned whatever secret is on this website. So that could be a problem. You can use JavaScript to make your own requests. So I think those are generally the main categories of things you might see in JavaScript. And definitely the alert and the requests are common things that attackers want to do. And finally, if you want to put all the pieces together, this is how a web browser receives all this stuff and creates a web page. So the first thing that happens is I receive the HTML and the CSS and the JavaScript from the server. All of this comes back to me in the HTTP response, right? So HTTP is the protocol for how to send and receive responses. So the HTTP protocol will send me this stuff, and the browser is going to parse the HTML and CSS first because these are easier. So this is parsed into something called the document object model, which is kind of a tree structure that contains all the elements. And then JavaScript will be interpreted. So now I execute the JavaScript, possibly changing some stuff on the HTML because JavaScript can do that. And then once that's all done, something called a painter comes along and draws out the web page for me. So it draws bit by bit, pixel by pixel, the entire web page for me. So that's usually how the web browser interprets things. And the document object model is just a model that lets us represent HTML as a tree, which is a little bit nicer to handle than just a pile of text. But the server does give me a pile of text, which is the HTML and the CSS and the JavaScript. And my browser has to execute the JavaScript. It has to parse the HTML into a tree, and that's how the web page is rendered. Okay. So that's putting all the pieces together. I think we have time for a break so that everyone can take a stretch. And I guess we'll come back at 4:38 to talk about security on the web. Does that work?
Sounds good to me.
Objections? Okay. And feel free to ask questions if during the break. Okay, welcome back. So we are now done with the intro to web. So all we've talked about are the features you have to know. And now we can start breaking stuff and fixing stuff and taking a look at what security on the web is like. So first we have to think about what are the risks on the web. So there are a couple of risks. The first one is if you're a web server, you're a computer serving things to lots of people around the world. So we probably don't want web servers to be hacked. So for example, Google has a web server. We probably don't want attackers to hack into the google.com web server because now when I search for something, maybe the attacker is going to feed me lots of viruses and bad things. So that's not good. And usually the protection to this is server-side security. So all this is maybe protect the server computer from being attacked. So make sure that the Google server doesn't have a buffer overflow vulnerability. Make sure that unauthorized people can't access the Google servers, or make sure that the Google server isn't using bad password hashing or something. So usually these are attacks that we've seen before and we'll see later, and they usually have to do with just protecting their computer. So same as protecting any other computer, but because these web server computers are serving the whole world, it might be more important to invest in security. But that's the first risk. It's kind of not too related to what we're going to talk about, but it is related to security in general, so still important. The second risk is if you visit a malicious website, so there are lots of attacker-controlled websites. Remember, anybody can create a website, including attackers. So lots of attackers have created very malicious websites. I'm sure lots of people here have visited malicious websites before as well, and you see how they have lots of very steamy ads or download buttons and very attack-y things. But the thing is, we don't want this malicious website to be able to damage our computer. So if I accidentally visit evil.com, oops, I don't want that to immediately brick my computer, right? I don't want it so that visiting one website completely destroys my computer. That would be very, very dangerous. And I don't know if I would use the web if that was the case. So one thing we do is something called sandboxing. So this is related to kind of least privilege, if you remember that from the first lecture. Basically, we say that the browser has protections so that the websites can't just completely destroy our computer. So for example, if you're running JavaScript, the JavaScript from other websites that come into us and are run by our browser cannot access files on our computer. So if I go to evil.com, evil.com gives me a piece of JavaScript that says, delete all files on your computer, it's not going to work because the browser is going to say, hold on, you can't do that. So someone asked earlier why Java, the language, branched into JavaScript because of the web. And the reason is this. So the reason is because Java was a very powerful language. Java could write files or delete files or do things to wreck our computer. And some microsystems people realized, maybe using Java on the web is a bad idea because now servers that are evil can give me malicious Java, and that could cause my computer to be destroyed. So instead of using Java, let's use something called JavaScript, which is a little more protected, and JavaScript can't do things like deleting our whole computer. So this is related to privilege separation or least privilege from the first lecture. And again, this also means that if you are eventually hired to work for Google or Firefox and you have to write a browser, you had better be very careful and make sure that your browser is memory safe and not vulnerable to any attacks, because if somebody can exploit the browser itself, now maybe they could get around JavaScript and take over your computer or something. So you have to be very careful if for some reason you end up working on a web browser. But fortunately, the web browsers we use have been developed over the years and they should be safe, but there are still security updates once in a while. So that's the second risk. And again, the protection is just to have the browser sandbox the websites and make sure that if you do visit an evil website, it can't destroy other things on your computer. So that's the defense. The third defense is, or the third risk is, if you have a malicious website, so if I go to evil.com, this website shouldn't be able to access other websites either. So we talked about how this website can't access our computer, but we haven't talked about how this website might be able to access other websites. That could be a problem. So maybe I have two browser tabs open. So I have one browser tab that's evil.com and another browser tab that's amazon.com, and I'm purchasing something maybe. Well, it would be a problem if the attacker on evil.com could just hop over to the Amazon window or the Amazon tab and start buying things or reading our emails or sending emails or whatever. That could be a problem. So we have designed a protection for this. So the original web designers did not have a protection for this. They didn't think about attackers, so they just ignored this problem. But now that so many people are using the web and there are attackers, we have come up with a new defense to protect against this, and it's called the same origin policy. And it's kind of what you would expect. Basically, it says the web browser has a new responsibility, and its responsibility is the evil.com website can't access amazon.com because they're not related. There's no reason why evil.com should be able to access Amazon, because that would be a security issue. So this is the same origin policy. So again, the same origin policy, it's just a rule that someone wrote one day. And all this rule says is one website cannot tamper with, it can't alter or change other unrelated websites. And we'll talk about what unrelated means in a minute. But this is a rule that the web browser has to enforce. So it's your web browser's job to make sure that if you have a bunch of different browser windows open, or if you're visiting 50 different websites at one time, which I always do, they have to make sure that any websites that are not related cannot access each other, because that would be a problem. Okay, so how does same origin policy work? So we have to talk about what is unrelated and what rules does the browser enforce. So it's actually a pretty simple rule, and you can follow it yourself as well. So the way it works is every web page now has something called an origin. And the origin is defined by the URL of the web page. Remember, every web page has a URL, right? Everything on the web is defined by a unique URL. So I can give every URL its own origin. And the way this works is it has 3 different parts. It has something called a protocol, which is the protocol in the URL. It has a domain, which is the domain in the URL. And it has a port, which is the port in the URL's location. So we've seen all these before already, but now we're going to write them out. And the set of these 3 pieces of information is the origin. So for example, here's a URL. This URL's origin has 3 parts. It says protocol is HTTPS, domain is tune.cs161.org, port is 443. So those are the 3 pieces of information that make up the origin. And one thing you might notice is that the path has nothing to do with the origin. So the path, the query parameters, the fragments, all of that is not related to the origin. It's only these 3 things. Here's another URL. This one has a protocol of HTTP. Domain is cs161.org. And wait a minute, there's no path or there's no port. So what do? I use the default. So if I'm using HTTP, the default port is 80. If I'm using HTTPS, the default port is 443. So those are just the default numbers. Okay, so this is the origin. So the first thing you do when you're running same origin policy is you figure out what the origin of the web page is. That's your first job. So once you have the origins, now you can start comparing web pages. And the way this works, again, very simple. All you have to do is take a look at your 2 websites. And if the protocol, domain, and port all match exactly, then they have the same origin. If not, they have different origins. So it's as simple as string matching. So you literally just compare 2 strings word for word. So here's an example. And this might bore you, which is good because it's a very simple rule, right? So prepare to be bored. Here we go. Here's the domain, here's another domain. If I want to check that they match, I just do some string matching. Here's the protocol, HTTP. Here's the protocol, HTTPS. Those are not the same strings, so the protocol doesn't match. Here's another one. Here's the domain, tune.161.org. Here's another one. It's only cs161.org. The domains don't match, so it's not the same origin. Here's another one. This one has no port, so it's default to 80. This one has a port, it's 8,000, and those are not the same number, so the port mismatches. So again, all you have to do is just perform string matching on 3 different parts of the URL. So check the ports, make sure those match. Check the domains, make sure those match, like word for word or dot for dot, and then check that the ports match, possibly adding a default if it doesn't exist yet. And that's all you have to do for same origin policy. It's literally just string matching. So if you know how to compare strings and check if they're equal, you too can perform same origin policy. So what do you actually do once you come up with this comparison? So what happens is if you have different origins, so if those 3 things don't match, then the websites are blocked from interacting with each other. So for example, evil.com and amazon.com have different origins. Why? Because they have different domains. So they can't interact with each other. So now we've solved the problem that if I am browsing Amazon while I'm on an evil website, the evil website cannot access Amazon's password or purchasing power. Another example is maybe I am on cs161.org and it embeds google.com. So remember the iframe thing, I could put a website inside a website. Well, because these 2 have different origins, because they have different domains, the inner frame can't interact with the outer frame, and the outer frame can't interact with the inner frame. So they're different origins. The origins don't match. So even though they're kind of on the same web page, they have different origins, so they can't interact with each other. The CS161 outside frame can't change things on the inside, and the inside frame can't change things on the outside. They are basically on their own. There are a couple of funny exceptions, so we'll talk about those quickly. And again, these are all just rules. So if you just follow the rules, then everything should work out. One exception is JavaScript. So sometimes you can load JavaScript from other websites, and there's an HTML tag for that. So for example, maybe cs161.org has fetched some JavaScript that's published by google.com. So it says, go to Google, fetch this JavaScript, and paste it here. This exception is kind of weird, but basically, the JavaScript actually has the origin of the page that loads it. So even though this JavaScript came from google.com, it's going to run with the origin of cs161.org. Kind of funny, but the way I think about this is basically what you've done is you've gone to google.com, you've copy pasted the JavaScript onto your website, and then you've run it. So, or you sent it to the user for running. So it kind of makes sense that, well, if the cs161.org people have asked to fetch JavaScript from Google, they are basically asking to copy paste Google's JavaScript into the website. So it should run with the origin of cs161.org. So that's the first exception. The second exception is images. We saw this too. Sometimes you can go fetch and display images from other origins. And this one is kind of weird, but the thing to know is just that the website itself can't really mess with the images. All it can do is resize the image. So if I am cs161.org and I go fetch the Google logo, I can resize the Google logo on my website. I can make it larger or smaller, but I can't go and change the Google logo on my website. So that doesn't work. So it's limited, right? And the final exception is maybe in some unusual case, you have two different origins, but they want to share a little bit of information. They want to talk to each other. So we do have a couple of protocols for very limited sharing. So we don't let them just talk to each other and do whatever they want. But if they both agree that I want to talk to each other, so maybe, I don't know, cs161.org wants to talk to cs162.org, and they want to share a little bit of information, there is a function in JavaScript to do that. And there's also a protocol called cross-origin resource sharing, where you can share a little bit of information if you need it. So that's just in case you need it, it's there. But again, it's very limited, and it's not for you to share everything. So it's not like they have the same origin and you can just do whatever you want. It's only a limited amount of sharing. But it is there as an exception if you need it. I think that's actually the end. So I am just about in time. So let's just quickly summarize everything, because these introduction lectures are definitely kind of just, let's just pile some information on you and then we'll sort it out later. So they are kind of dense, but we are done. And now we can finally talk about security. So again, the first thing we talked about are URLs. And we said every piece of data on the web is identified by a unique URL. And the URL has a bunch of different parts. It has a protocol that tells us how to retrieve the data. So use HTTP or use HTTPS or use one of the other ones. Then it has a location that tells us there are 1 million web servers in the internet or on the web. Which one should I contact? The location tells me which one. And if I want to, I can also add a username or report. The path tells us, well, I've picked a web server, but this web server has lots of different services and files. So I want to pick a single path. And this is often can be thought of as like a file system. So the web server has a file system, and I'm going to navigate its folders to pick a file. Then there are a couple of optional ones. So if you are trying to ask the web server for some fancy computation, you can send it some queries. So those are arguments separated by question marks and symbols. Or if I want to skip to a section of the website or do some browser side processing, maybe I can add a fragment, which is added with a hash sign. So those are kind of additional things you might see sometimes. And we also said that if you have special characters in your URL, you probably want to escape them. So that's URLs. I think I see a question and I have time. So someone said different pages are usually different processes. Yeah, so that's true. So if you go all the way back to how we talked about sandboxing, the browser does tend to sandbox windows or sandbox browser tabs, making sure that if you have two different tabs open, they run in different processes. And I think we'll see that again tomorrow. But that is definitely something that browsers do for sandboxing. So yeah. Anyway, back to the summary. So the next thing we talked about is HTTP. This is a protocol. So when we're talking to web servers, we have to do a little bit more than just saying, here's my request, and just flood it with bytes. And then the web server says, here's my response, and just flood you with bytes. That would be very ugly. So we have some structure introduced to make the request and response a little bit cleaner. And this is called HTTP. It's a request response protocol. So the way it works traditionally is you make a single request, the browser gives you a single response, and it's always one-to-one. And in an HTTP request, the main things that we're looking for are first the method. So choose a type of request, usually get or post. Get is for things that don't change state. Post is for things that do change state. Then we give it a path. So identify a file or a service that I'm looking for. If I need to provide arguments, then I'll do some query parameters. And finally, if I'm making a post request, I'm asking it to change something on the server. So I'll probably give it some data. And because a GET request doesn't change the server state, it's just asking to give me a resource, I usually will not include data. So that's the request. Then we talked about the response. So the response also has the protocol name, which is just HTTP, and then says, here's a status code to tell me what happened. So was it a 404 not found? Was it a 200 OK? Was it a 403 forbidden? There are lots of different ones. But status code is a number that tells me what happened. And then if there's some data, the data can also come in the response. So that's the request response model. And finally, talked about some parts of a web page. So there's HTML that can do a bunch of things. It can create links, forms, images. It can embed other websites inside. So HTML gives us a way to create documents that look pretty in web browsers so that we're not just staring at plain text. But again, you don't have to know too much about the rules of HTML. Just know that that's what HTML is. And if we do ask you about HTML's stuff, we'll usually give you the syntax that you need. CSS is a style sheet language. So HTML by itself is kind of ugly, but if I want to define colors or appearances, or maybe the buttons should look a little bit different, then I can use CSS to do that. And CSS is pretty powerful. So if I use it maliciously, it is basically as good as JavaScript. And finally, JavaScript is the programming language. So this is used for running code in the web browser. So again, the server is not running JavaScript. It has some JavaScript code. It sends the code to us in HTTP, and I receive the code, and I run the code in my browser. JavaScript is very powerful because it can modify anything on the web page can be modified in JavaScript. It can create pop-up messages. It can even make its own requests if it wants to. So JavaScript is very powerful. And then we talked a bit about different risks in web security. So we talked about how if servers can be hacked, we need to protect our servers. If a malicious website wants to destroy my computer, my browser needs some sandboxing so that the website can't just immediately access files on my computer and delete them. And we talked about how two websites should not be able to talk to each other if they're not related. So evil.com should not have the power to talk to Amazon.com because they're not related. So the browser now has a rule that it has to enforce, and it says two websites, if they have different origins, they can't talk to each other. If they have the same origin, they can't talk to each other. And the rule is two websites have the same origin if those three things match: the protocol, the domain, and the port. And again, it's literally just checking that the strings match with the single exception of if the port is not specified, you default. But otherwise, you just check that the characters are exactly the same and you match the strings. And then we talked about there are a couple tiny exceptions. So JavaScript runs with the origin of the page that loads it. So if cs161.org loads google.com JavaScript, it is basically copy pasting JavaScript into its website. So it runs with the origin of cs161.org. We also talked about web pages can fetch images from other origins if they want, but usually they can only resize them. They can't mess with the image. And finally, if for whatever reason there are two websites that are different and they both agree to do some sharing, there are some ways for them to do a little bit of limited sharing. So that's called cross-origin resource sharing or post message, but you don't have to worry about that too much either. And it looks like we are just in time, so unless there are any final questions, we will see you all tomorrow for more web security. Okay. Don't think there are any questions, so let's stop the recording.